Hello and welcome back to another part of our reusable rocketry course here on Mathativity. So in this part we're going to be looking at modern rockets that aren't reusable. And so after our last part, the history part, you might recall that we came out in the modern world with sort of two big rocket manufacturers, booster manufacturers on top, which are the Russian Federation, which was the biggest part of the Soviet Union, and the United States. So in this part we're going to be looking at 4 different rockets, 2 from Russia and 2 from America, and we're going to look at sort of some of the design problems they face and how that impacts reusable rockets. And also we're going to just sort of be talking more generally about rockets, things like Newton's third law and problems with ignition and something called coking, which we'll talk about later. Right, so the 4 rockets we're going to talk about are the Proton, the Soyuz, the Delta IV, and the Atlas V. The Delta and the Atlas are American, and the Proton and the Soyuz are Russian. Okay, let's tone it back a bit from there, and let's talk about the fundamentals of how a rocket works. First up, Newton's third law. Newton's third law is quite old. It was discovered by Newton in, I believe, the 1500s or 1600s, and it states that every action has an equal and opposite reaction. You've probably heard it before, but it basically means that if you push down on something, if it doesn't move, it will push back on you with exactly the same force. So if I push on a car, the car pushes back on me with exactly the same force. So if I push on a car and it doesn't push back on me with that force, then I'm accelerating that car and providing it with a force, which is the reaction. So that means if you have a rocket and you use a rocket engine to throw something out the back at super high speeds, then that force will provide you with a reaction upwards. If your action is downwards, then your reaction will be equal and opposite, upwards. In order for this rocket engine to work, it needs fuel. And usually we use things that burn. I know that sounds obvious, but things that burn have a special property to them. They combust with oxygen. They react readily with oxygen to create some product which then gets blasted out the back of the rocket at super high speeds. So this can be hydrogen and oxygen, this can be kerosene and oxygen. You might hear kerosene referred to as RP1, that's effectively enriched kerosene, rocket kerosene. So most fires work like this, but specifically in rockets we need a super concentrated amount of oxygen, and because rockets tend to operate in the vacuum of space where there's no oxygen, they carry it on board as liquid oxygen, usually cooled gas to such a low point that it literally becomes liquid oxygen. So if you burn, let's take kerosene as our example here. You take kerosene from your fuel tanks, you pump it into a place called a combustion chamber, which is where the burning happens, where it combusts, and you pump the liquid oxygen in too, but they don't burn. You need a ignition to set them off, something to set them on fire. And you might think, well, it's not that hard, right? You just stick a lighter in there or something and set it to be automated, maybe. But it doesn't work like that, because the lighter, it depends on oxygen and fire, and it needs to start somewhere. So what lights the lighter? Maybe a lighter. What lights the lighter's lighter? You end up in this sort of infinite cycle. So the first rocket we're going to talk about is the Proton, which solves this problem in an interesting way. It's a Russian rocket that's designed not to carry people, it's just to carry cargo or satellites. And it has a special solution to this problem. It is a bipropellant, which means it has 2 propellants, as most rockets are. Usually one of them is oxygen, but in the Proton it's not. It uses 2 fuels, unsymmetrical dimethylhydrazine and dinitrogen tetroxide, but you can shorten them to UDMH and NTO. And these are special not only because they're highly toxic and highly volatile, but because on contact with each other, they explode violently. And that means that the proton doesn't need a proper ignition system. It just needs to funnel these two fuels together, and they will burn on contact with each other and light up the engine. Which is really helpful and really handy. So that's how the proton ignites, but what about something that does have oxygen as its fuel? Something like the Soyuz rocket, which we're going to talk about now, which uses kerosene, well, RP1 technically, and liquid oxygen as its fuels on the main stage. Now, the Soyuz has been in use for a while, and it is lit in the most fantastic way. Actual wooden sticks in 20 of the main engine bells, which are set on fire before launch, and then fuel is pumped onto them so that they ignite. They are literally sticking a match into the Soyuz combustion chambers so that they light before launch, which is honestly hilarious. But there's actually a really big problem with kerosene, which we're going to talk about now, actually. And if you're familiar with chemistry, then you might know that kerosene is sort of a mix. It has some very long chain compounds in it. And if you, under certain conditions usually found in a rocket engine, these long chains will break apart and form smaller chains, which they like to bond with the sides, the pipes, and the combustion chamber of your rocket engine. And if you have a blocked pipe in a rocket engine, that's not going to end well. Imagine if your exhaust pipe was totally blocked up in your car. That would not end well. And on a rocket engine, of course, it's much worse, because these are gigantic machines. So, in order to solve this coking problem, well, of course, you can not use kerosene, which we'll talk about with the Delta 4 in a moment. But you can also design your pipes in a very specific manner using very special metal techniques, metallurgy techniques, to make it so that coking doesn't stick to the side of these pipes. And that is what the RD-180 does on the Atlas V rocket. Now, the Atlas V is absolutely phenomenal. Its engine is the RD-180, and that's produced in Russia. And it's a phenomenal engine, because Soviet metallurgists, when they were making this engine, the Americans thought that it's too difficult to create a metal alloy that is just on point to avoid this coking problem. But the Soviet metallurgists did it, and they created the RD-180, or a predecessor of that, which has a perfect blend of sort of nickel and chromium and cobalt and other sort of early transition metals like that, that can specifically avoid this coking problem. And that's why Russian engines are almost 10% more efficient than their American-made counterparts. And that's a really important reason for international cooperation in the area of space. And the Americans build the rest of the Atlas V, sort of the more aerodynamic parts, and the second stage, the Centaur upper stage, which uses the RL-10, which is an American engine. And it's also super good, because apparently the Americans are really good at vacuum engines. Anyway, it's all very complex and interconnected. You can't really make generalizations like that. I know the F-1 is an American rocket, not a Soviet rocket, but it's certainly incredibly efficient, incredibly powerful, and really, really good. Of course, as I said, let's quickly talk about the Delta 4 rocket, how it doesn't use kerosene. That's how it solves its coking problem. It uses hydrogen, liquid hydrogen. And liquid hydrogen is an awesome fuel. Now, of course, it did create the Hindenburg disaster, which is not a great thing, all things considered. But it's awesome as an awesome fuel, because if you take two H2 atoms, so you've got 4 hydrogens, and 1 oxygen, an O2, you can combine that into 2 water molecules, H2O. And that is the only product of your rocket. Water, steam, right out the exhaust, which is super good as a rocket engine, because then you can accelerate it super fast because it's very light, and you can get massive amounts of efficiency out of it. So the Delta rocket is super efficient, and it has none of these coking problems because it doesn't use kerosene as its fuel. Of course, hydrogen has its downsides. Because it's so light, it's the lightest chemical element, it is very sparse. You need gigantic fuel tanks to hold it even when it's in a liquid form. And you have to get hydrogen very, very cold to make it liquid. So, those are the 4 rockets, and those are some problems. And I'd like to point out something quickly, because this is, of course, about reusable rockets. And the Merlin engine on the Falcon 9 that SpaceX makes, that most of these engines can only be ignited once. And the Falcon 9 it turns its engines off halfway through flight and then turns them back on for landing. So it needs a very special way to light up its fuel, light up its engines, and I suppose its fuel, so that it can do this multiple times. And in fact, the Merlin engine has to ignite 4 times on its launch to landing, which is a very large amount for a first stage booster. So we'll talk about that in the next part, which is going to be talking about reusable systems. We'll also talk about a bit about the shuttle and why you should use reusable systems over these ones we just talked about, expendable stages, where the first stage just drops into the sea. So that's cool. I think I've covered everything. See you then.